I'm going to show you how to do a gravitational potential and kinetic energy problem here. So we have a ball that's elevated at a height of 1.5 meters. It's going to roll down this ramp and then up this one to a final height of 0.5 meters. And what we're going to do is determine the total amount of energy in this system, and we're going to find the velocity at point A, point B, and point C. So the total amount of energy in these problems is your kinetic energy plus your gravitational potential energy. Now, when you become more advanced, you will learn that kinetic energy actually has a translational component and a rotational component. However, we're going to simplify matters and ignore the rotational component for now. You can learn about that next year when we do grade 12 physics. However, for now, we're just going to assume that if you assume the radius of that ball is relatively small, then you can ignore the rotational component of your kinetic energy. So at point A, point B, and point C, we're going to have a consistent amount of energy throughout this problem. We call that the conservation of energy. So the total energy is the kinetic energy, which is half mv squared, plus the gravitational potential energy, which is mgh. However, if we're setting this ball up and letting it roll from the top, the initial velocity is 0. So when we're at point A, our total energy is 0, that's 0 kinetic energy, plus mgh, where m is our mass, and in this problem our mass is 2 kilograms. G is acceleration due to gravity, it's 9.8. And h is our height, and as you can see from here, our height is 1.5 meters. So the total amount of energy in the system is 2 times 9.8 times 1.5. So we have 29.4 joules of energy. Now when we go to point B, so this ball has rolled its way down, so it is now a 2 kilogram ball that's down here. It's moving fast and it's low to the ground. Our total energy is again our kinetic energy plus our gravitational potential energy, but when we're on the ground, our height is 0. So that means the gravitational potential energy is 0. So our total energy is our kinetic energy. We know our total energy to be 29.4, and we know our kinetic energy to be half of our mass, and remember our mass is 2, times the square of our velocity. Well, if you do a little bit of algebra to this, you will see that 29.4 is equal to the square of the velocity, or the velocity is the square root of 29.4. So our velocity is 5.4 meters per second. So, recapping, we started out up here using height and mass and 9.8, and the fact that it wasn't moving, we found the total energy in the system to be 29.4. After it's rolled down to here, our height is 0, so there's no longer gravitational potential energy. All of the energy has gone into kinetic. And our kinetic energy is half mass times velocity squared. In this simplified case, to be realistic, let's assume this is ice, so it's not actually rolling, it's just sliding. And so as it slides its way down, all of the energy goes into what we call translational kinetic energy, or the energy associated in this body moving along, not spinning. Now finally at point C, we're at a height of 0.5 meters. See that? So we now rolled our way back up to 0.5 meters. And if you're in my class, you remember when we went to the skate park and rolled a bowling ball down a ramp and then plotted that graph, we saw that as it went up in height, it went down in speed. So it's going to slow down. What's happening here is the total energy is the same, but that energy is a mix of kinetic energy and gravitational potential energy. So let's write out everything we know at point C. We know our height is 0.5. So we know that our gravitational energy is our mass times 9.8 times our height. So the gravitational potential energy is, I was about to use my calculator, that's stupid. 0.5 times 2 is 1, so our gravitational potential energy is 9.8 when we're at that height. We also know that our total energy is 29.4 because in this problem our total amount of energy does not change. So, knowing that the total energy is the kinetic energy plus gravitational energy, our kinetic energy is our total energy minus our gravitational potential energy. So it is 29.4 minus 9.8. So our kinetic energy is 29.4 minus 9.8. It is 19.6. So 19.6, our kinetic energy is half mv squared. So it is 19.6 is 1/2 of 2v squared, because our mass is 2. Those cancel each other out, and our velocity is the square root of 19.6, which is 4.4. We have a velocity of 4.4 meters per second at this point. So let me recap. We have a ball. It started up here and it slid its way down to here and then up to here. As it made its way down, it lost gravitational potential energy but gained kinetic energy. So when it was up here, it was all gravitational energy. When it was down here at the bottom, it was all kinetic energy. And when it was part way up, it had a mix. It had gravitational energy because it was elevated to this height, plus it had kinetic energy because it's still moving. The total energy is the same at each stage. There's no energy lost from this system. To be realistic, there'd be a bit of energy lost in terms of friction. So things would heat up and the overall energy you would see drop, as we saw experimentally. But in the theoretical problem, just keep energy the same. Determine, there'll be a clue as to whether kinetic energy is 0 because it starts out staying still, or gravitational energy is 0, or it's a mix between the two.